Welcome back. So we have been revising whatever we have been doing for the last few weeks in this discrete math course. So today we'll be focusing on graph theory and the linear programming methods. The most important thing here is modeling. One of the ways of attacking problems uh, is modeling the problem in a very nice, usable mathematical language. Now, one can use different mathematical languages to model, or one can use different models, and depending on the structure of the problem, one has to decide which model to use. In this course, we have looked at two particular models. Number one is graph theory, number two is linear programming. We have spent quite a lot of time on graph theory, but graph theory as a whole deserves a full course in itself, and hence just a few weeks on graph theory is not going to be enough to do justice to this subject. But in any case, we did an introduction to graph theory. So let's quickly recap what we have. So first of all, graphs are a set of vertices and a set of edges. The edges kind of denote the relationships, the binary relationships between vertices. The vertices are elements of some set. And given the set of vertices and the set of edges, we have the graph. So the graph is used to represent binary relationships. If the graph is symmetric, we call it undirected, or if the relationship is symmetric. We can also have weights assigned to each of the edges, and that is called a weighted graph. We have the notion of what the neighbor is and the degree of a vertex. So in fact, we represent this graph by drawing on the plane where these blobs represent the vertices. The edges between them are drawn by lines that join the two vertices which they are supposed to represent. We can have weights on the edges. We can also have direction on the edges if the original binary relation is not symmetric. The advantage of this graph is that it's a nice mathematical way of expressing relationships between objects. They are very simple and very general. We have seen this example of many problems in real life can be designed as a problem in graph theory, and hence studying the structure of graphs and designing algorithms of graphs is an important field in the modern world of algorithms and complexity. Now there are quite a number of properties that keeps on arising again and again, and we have special names for these. So we have the definition of paths, which basically, if you have to look at a path from G to A, it's a set of edges, it's a path from G to A. There can be various paths from G to A. Paths can be directed or undirected. And we have a notion of connectivity that we looked at. And the notion of whether U is connected to V, that means if there is a path from U to V, is an equivalent relation, and hence the graph can be written as a disjoint union of connected components. We have also seen cycles like this, and we also have looked at some cases when cycles exist. And if a graph is not cyclic or doesn't have a cycle, it's called a tree, and a connected graph without a cycle is a tree. A tree is a very useful notion again. So these are small notions of graphs that we have seen, or various properties of graphs that we have seen in this course. We have gone through various of these examples. Right. We have seen nice properties of trees. For example, a tree has has a degree 1 vertex. If you remove a leaf from a tree, then it's still connected. And we have also proved that every graph has a spanning tree, that is the tree that touches all the vertices. Now we can also define other structures in graphs, namely sets and cliques that we have defined. So independent set is a set of vertices such that there is no edge between any pair of them, and a clique is the opposite of that. So in other words, here is a set of the red vertices are sets of independent sets, and we can have cliques. And now there are a lot of applications that one can apply. One can model using graph theory, and I'm not going to go through these applications one by one, but please go back and refer to the original videos in the original places. So we can use the concept of coloring, whether when we are allowed to color a vertex with some k colors such that no two neighbors have the same color. This is one more concept in coloring that is very useful and very handy, and it is used to and is studied a lot. We call it the chromatic number of graphs. So here, for example, one can color this one with 4 colors. Coloring has applications in drawing on coloring of maps, and we also looked at some problems and properties of coloring. Thus, graphs are very useful for modeling various problems. Studying graphs is an important subject called graph theory. People who have attended this course, I strongly recommend you to go and learn a little bit more on graph theory, possibly attend one more course on graph theory. It's a subject that deserves a whole course, and it's a beautiful subject that is very useful for solving real problems, mathematical problems as well as real life problems. We have studied a small number of properties of graphs, and we have of course used the proof techniques of induction, contradiction, case studies, etc. to solve properties of. Now one more model that is used extensively is the linear programming model. The idea is that you can maximize or minimize a linear equation under a set of conditions, and this is called the linear programming model. Now this linear programming model linear program can be solved if the variables can take real numbers. This is called linear programming, and it can be solved very quickly using various softwares. For example, in R, there is a very simple way of solving it. Now, linear programming is again another subject that is very well studied, and many different algorithms are solved using linear programming. If the variables are reals, can take real values, then it can be solved in polynomial time. But the trick is, of course, how do you model it in the LP form? So many optimization problems can be formulated in this linear programming format. But if the linear programming, the variables are over integers, then unfortunately it is not necessary we can solve it using polynomial time. In that case, there are various tricks to solve them. The subject of linear programming is a very vast subject, and we didn't do too much work in this course on this. The main idea was that can we or how can we model it using linear programming. So in this course we spent quite a bit of time on how to model a problem using either graph theory or linear programming. Now how to solve such problems is something that I have not done exactly in the class, and unfortunately it will require an independent set of courses on linear programming and on graph theory to solve them. So I again encourage you guys to attend these courses. So to conclude this particular revision, many problems can be modeled as graph problems or linear programming or optimization problems. There's a lot of things known in the literature. The trick is to model the problem in a mathematical way for which techniques are available. Thank you.